Okay, thank you for the stage. So, thank you for the introduction. So, my name is Rolands Cepuritis, and I represent Primekss North America here today, and I will tell you about technology we have developed to save embodied carbon in different kind of structures, but mainly in different kind of slabs. So, the technology has been developed by company Primax. So, originally coming out of Riga, Latvia, which is in northeastern Europe, and then expanded, has been expanding throughout the years in the world, and already for 10 years we are offering this technology also in North America, in the United States and in Canada. And I will tell about this technology in a bit generic way, mainly through the examples of how you apply it to slabs on ground, but in fact you can apply it to different kind of structures, also slabs on piles, slabs on insulation, mat foundations, and then we've also developed over the time different kind of layered slab structures. And when we developed this technology, we had two main things in our mind. One, we wanted to have a technology that enables embodied carbon savings, and also a technology which offers drastic reduction of construction and contraction joints, and offers slabs that are dimensionally stable over time, so that they are especially suitable for different kind of future automation applications. But if we move forward to the technical part, so the technology is called steel fiber reinforced self-stressing concrete. So to understand how that works from technical perspective, let's look at something that is kind of more known, and that's regular post-tensioning technology. How does that work is that we put in a steel tendon in a concrete element, let's say it's a beam, and if the tendon is just there, it's laying in some kind of canal, which is not, or tube, which is not in direct contact with the concrete, and we apply a load to that element, the element would start to bend, and this tendon doesn't have any function there. If we stress this tension and then transfer the load from this tension to the concrete through tendons, and you can see a picture of a typical tendon anchor there on the right from your point of view. And this tension from the tendon is then transferred to concrete. And concrete is first put in compression, and then also you can get some pre-camber in this element. And then if we apply the same load, given that everything works as in this schematic picture in terms of the relations there, then under the same load, the element would not have a deflection, it will have a neutral position. This technology is very good, and what it allows you to either have a longer span at the same section depth, or it allows to reduce the section and have the same span. It also has some limitations, and the limitations are mainly economical, and from the execution point of view, it's quite expensive to install these tendons. Also, if we talk about slabs on ground, if they are there, it makes the pouring of the slab more cumbersome. Most likely you will need to pump the concrete. Also, you are limited to when you could put the slab in service, because it takes time to stress the tendons after the concrete is hardened, and apply the load through the tendon anchors to the slab, etc. There are some limitations to that. So we look to something which is more simple and more economical, and that is chemical post-tensioning. So it's the same principle, but instead to tension the steel element in the concrete, we use the concrete itself. So many of you have probably heard about shrinkage compensating concrete. This is what is developed through the ACI Committee 223. So that's a concrete which, in contrast to the regular concrete, during the curing period, it expands to some extent and then shrinks back to original length. But you can apply different type of chemicals, self-stressing agents, and then you can make the concrete expand much more, so that it doesn't shrink back to its original length of the element. And then if there is some steel in the concrete, self-stressing concrete. This steel can be put in tension, and then, of course, as the concrete is still there, concrete is put in a compression. So the principle is the same, just that you use concrete itself to pre-stress the element. The idea is not new. There's a French engineer, Lossier. He came up with this idea in 1930s, and here's one example I like to show. This is from his work. So he wanted to make out a beam out of this kind of concrete. So he made beam of two regular concrete elements. There was a connecting steel rebar. I think at that point rebar was mainly smooth, so you needed the hooks to make some kind of bonding between the concrete and the the steel. And then in the middle, in this part, he made this self-stressing concrete. So this would expand and then push these parts of the concrete apart and stress the steel. So a very brilliant idea. But back then they concluded this is too hard to control. We can't control it, so it was forgotten, and people didn't use this principle to make structures for a while. What we did at Primekss, we understand that to control it, you need to control the whole value chain of this concrete part, of the self-stressing concrete part. So what we do is that we look at the raw materials to make concrete self-stressing agents, and then we control the pyro processing and grinding part. We have a plant where we batch all the ingredients together, and then for every single project that we do, we control the final concrete mix so that the binder system we use is compatible with the self-stressing agents. And then in the end, to conclude the technology, we put in steel fibers. So we use a relatively high dosage for the industry standard, premium quality, high tensile strength steel fibers to restrain the expansion and put concrete in pre-compression. So that's the backbone of self-stressing steel fiber reinforced concrete works. So we also monitor the expansion on site with different types of sensors, and then through the mathematical approach we have developed, you can actually recalculate the in situ expansion, taking into account the restraint and other properties into the pre-stress you are generating with this system during the curing. And there's of course also some math involved, but as was said by the publisher Stephen Hawking, every equation helps yourselves. So I'm not going to show you the math, but we have a model how we look at that, and we published it last summer in the magazine of the British Concrete Society. I think it was June issue. It stands somewhere there, which issue that is, but you can find the model that we propose to use for this in this publication. But how does that technology allow you to save embodied carbon? So if we look at the, for example, slab on ground situation, one thing is that in many cases the thickness depth, the section depth of slab on ground is just dictated by the fear of curling. So many instances you make slabs very thick just because you think they're going to curl, because there will be too big gradient of the relative humidity between top and bottom, and also there is some perception that you need some slab weight to prevent it. So when it's chemically pre-stressed, and you can compensate first of all, of course, you pre-camber it to some extent because it's typically more expanding on the top than to the bottom part, but also you don't get a big shrinkage deformation gradient, and in that way you are not limited to curling problems when you choose the slab depth. The other, of course, is the structural part. So you have a typical situation of a slab on ground or any kind of slab, and you put it in flexion. So typically you have the tensile on the bottom and situation, and then there's compression zone on the top. And if you add shrinkage to that, it's going to shift the natural axis of your slab upwards. But if you can add the part of this expansion part, and as I said, typically it's a bit more on the top because it's better moist curing there. Then you can actually shift the natural axis downward, and by this principle you can also optimize the structural design part and reduce the slab thickness, which is a big driver for the embodied carbon. However, we are taking much further, and I will show you what else you can do with this technology from perspective optimizing the embodied carbon coming from the binder system. I will show that through a practical project we did this summer. This project was done in Finland. So Finland is a country in north of Europe. So one side here is Sweden, other side is Russia. And we did a project in the Helsinki, which is the capital area for Makita. It was a warehouse. So here is just some pictures from the project, so you can see it's a real project. What is very important for the technology is proper moist curing. So we use a concept of 14 days moist curing that we have developed. But what is important for this project is that here's the binder system we use for that project. So here, every time I came to ACA conventions last years, you were talking about the type 1L cements where there is some percentage of limestone. So in this project we use a composite cement. This is according to European cement standard. And this is CEM2 BMSLL cement. And this means that about 35% of the Portland clinker has been replaced with limestone and slag. And on top of that, part of this cement also we replaced with pure fly ash, and then we added our self-stressing agents. So when we look at the binder composition for the project, it had only a clinker factor of close to 0.5, a great reduction. And if you look back at the work done by Lossier in 1930s, where they said that you can't control it, in this case we were able to control it in a quinary binder system. So typically you talk about like a binary or tertiary binder system, so this is a quinary one. I didn't know how to write it. I had to look into Google, how do you write a 5-component binder system. It worked out well in the way we applied. Of course, you get some other benefits when you apply it. You can not only reduce the cross-section and by that greatly the embodied carbon, which you can cut further by the Portland clinker reduction. You can reduce the joints. So in many instances there are no joints at all. And also if there is joints, they are not dominant because they don't open. So if you look from perspective of the user, you go from joints to no joints at all. How much carbon can you save? So 50% is possible, sometimes even more. And here's a real case study from North America. I think this is the one one of the latest projects we did. This one is in Windsor, Ontario, for general contractor Braccolini. The developer was Panattoni, and the end customer was Amazon. It's not a super large project, 110,000 square feet, and the defining loading there were a point load of 17 kips, or about 75 kilonewtons. So, and here's the comparison of what we were able to achieve on this slab. So, original design, which was there before we arrived and offered to consider our technology, which was important for Amazon because they like to save CO2 on their projects. So, the original design was 178 millimeter, 7-inch thick slab with a number 5 rebar reinforcement at 300 millimeter spacing, or 12 feet. And we were able to cut down it to 4 inches, and the dosage of the steel fibers was 78 pounds per cubic yard. And of course you can imagine that you compare these, you can see where a lot of the savings come from, of course also from replacing the steel, but we had a verified GVP savings of 38% on this project. And most projects are around there, some are 50%, some are even more. To sum up, so how do we achieve savings in this technology? We can, well, first of all, we use steel fibers. I mean, I was looking at a lot of sessions today already that explained, also in this session, why steel fibers are more beneficial or fibers at all compared to rebar in terms of embodied carbon savings. We can make these steel bars from green steel. So a typical number for fibers is, let's say, for steel fibers, I think it was mentioned in this session, for example, 1.2 tons of CO2 per metric ton of steel fibers, so we can apply fibers that cut down it to 0.3 tons per ton of steel fibers. We use chemically self-stressing concrete. We can replace quite substantially parts of the Portland clinker. And of course, as we reduce the thickness and we make large daily castings, this process is very effective. That's also contributes to CO2 savings. So in the end, we can save up to 50%, in some limited or some selected cases even more. And I like to talk about this roadmap by Global Cement and Concrete Association. How will we arrive at net zero structures by 2050? So one considerable part there, I'm not sure you see from here, I think this one is dealing with design. So it's saying that in order to arrive there, we need to think about more effective design. So we think that we arrived at that goal that they set to reduce there by 2050. We think we arrived at that already today with this technology. So yeah, this was in a nutshell what this technology is and how you save CO2 with that. So thank you.